All right, any other questions about anything before we move on? Okay, we're gonna finish 1.5 shortly here, so you'll see a due date for that on Canvas sometime today, or I'll put it up today, it won't be today. Other than that, the quiz tonight, and then I think that's it coming up. Our first test is going to be the 2nd of February, so that's a Wednesday. I think that's a week from this coming Wednesday. Still a little bit of a ways out, but I wanted to let you know about it. I also changed the due date on, or yeah, changed the date on that in Canvas. All right, I think we talked about this idea a bit. It's very important for where we're about to go, so I want to make sure we're still on board with it. So I have a function I'm telling you is continuous on an interval, closed interval 0, 4. And I'm telling you what the function is valued at either one of those endpoints. So are we okay with, I think we came to a consensus on these 3 things here. There might be a value where the function, or there might be an x value where the function takes the y value of -2. There might be an x value where the function takes a value of +1, but there must be a place where the function takes a value of 5. Are we okay with this? Okay, so, and hopefully, and I do this to kind of show you that in large part, this is kind of an intuitive thing. So very important theorem in calculus is called the intermediate value theorem. So I gave you a concrete example. Basically, here are all the generalities that we can kind of, as long as you meet these conditions, then I can guarantee something else happening. So here are my 3 conditions. I have a function that's continuous on some closed interval. The ends of those intervals have to be different. And as long as I have some number that's in between whatever those 2 values are. And when I say between, did we talk about the difference between and strictly between? Yeah. Okay. So it has to be not equal to f of a or f of b. It has to be strictly between them. If I meet all 3 of those conditions, then I can guarantee that this will happen. We're still on 1.5. This is the very end of 1.5. So as long as I meet those 3 conditions, this is true. There is a real number c. So when they want to make sure here, is the interval that I just showed you the same as the interval I showed you at the top? No. No. What's the difference? Brackets. So yeah, brackets. Yes. Well, what is that mathematically? What does that mean? Go ahead.
It means if they're brackets, then both those numbers are included.
Right.
Or parentheses.
Right. So a and b are not inside this interval. So if I meet all the conditions, then I have to have some real number c on that open interval such that f of c equals n. So it's called the intermediate value theorem because that's what capital N is. I picked a number in between 2 y values, and provided the function is continuous and I meet all these conditions, there has to be some x value where the function can take that x value and deliver that y value. So I think with the concrete example probably made a lot more sense than it does with this abstract general thing. Ask me whatever questions you have. We'll do an example or 2 here, but go ahead.
So that second condition is basically saying, like, say the interval is like 3 and 6. It's like f of 3 cannot equal f of 6.
Yeah, so I'll give you an example here. I mean, it's gonna look kind of silly, but it's worth thinking about. Let's say I had a function that maybe I care about the interval. What do we do? 1 to 5 before?
Yeah.
Maybe f of 1 is equal to f of 5. In this case, what are the intermediate values between f of 1 and f of 5? There are no values between f of 1 and f of 5. So it's called the intermediate value theorem because it has something to do with all those y values that land in between where the endpoints are. If I don't give you any y values like that, I can't make any use of this. Good question. Anything else? All right. So I want to show that this polynomial has a root between 0 and 1. So I want to try to make use of this intermediate value theorem. So let's just go through the conditions. What's the first condition of this intermediate value theorem? Go ahead.
Are the F of 0 and F of 1 don't equal each other?
Okay, so that's one thing I should check. I need to know that f of 0 is not equal to f of 1. What's f of 0? -1. What's f of 1? 13. So we're good there, right? I showed that the endpoints are different. What else do I need to check? Go ahead.
That between that interval, f has to be continuous, which
Alright.
is because it's polynomial.
And what do we know about polynomials?
They're always continuous.
Okay, so f is a polynomial. So it's continuous on 0, 1, right? And a lot of other places, but this is all I care about. I got some interval 0, 1 where it's continuous. I thought I wrote that straight over here. What else we need to check? This is a little bit, so these two, yes, these are important. The last one's a little hard to see how it matches up here. And maybe it's because, do I know what a root is of a function? What's a root?
That's
Or what's it?
X value, where it's like that.
Well, root is an x value, but how do I find them?
factoring.
I'm not gonna factor this, that's
Well, yeah.
be nasty.
You said the equation equals 0.
Right. So a root of a polynomial or any other kind of function really is where the function equals 0. So I'm looking for where, let's unpack this word root here. Where does the function equal 0? So I want to use the intermediate value theorem to prove that I have a root here. So look at what the endpoints of the interval is, what the endpoints are. I know my function is continuous on that interval. Is this going to help me find a root? Why is that?
And one of the numbers is 0 already.
What's that?
Because the interval already starts on 0. Is that going to be a root?
So that the 0 in like the first bullet up there, that's 0, that between 0 and 1, those are x values. So, and that's kind of a confusing thing here, but I'm looking for f of x equals 0. That f of x equals 0, that's a y value, right? Is value have something? I could, but that's gonna be very hard to take to solve. Right now, all I'm trying to do is, and that's gonna be a hard thing to get used to with this question is, I'm not asking you what the x value is. I'm just asking you to prove that there is one. So condition 1, show that the endpoints are different. Got it. Condition 2, show the function's continuous. It's a polynomial, so it must be. The last thing is I have to have a y value that's in between my two endpoints, right? Is 0 between my two endpoints?
Yes.
Yes. So that's the last condition.
So is the root of any function always where it,
Yes, that's the definition of what a root is.
okay, so there's like a lot of them that probably don't have a root. Like a lot of functions out there that just not.
Oh, right. Yeah, like y equals x squared plus 1 has no roots.
Okay, alright, that's-
But this one, based on the conditions I've given you, I'll just say this here. -1 is less than 0, which is less than 13. So those are all three conditions of the intermediate value theorem. The endpoints are different. The y value I care about is in between those two endpoints. And it's continuous on that interval. So because of all those things, then what does the intermediate value theorem tell us? There is a root of f of x, of f, on what interval? 0 to 1, yes, be more specific though. Yeah, it's open, right?
Yes.
I mean, I know it's not a 0 or 1, I would have found it. I definitely looked there. So basically I'm saying this for, f of c equals 0 for some c on that open interval. And that's all I asked for. I'm not asking to solve for it. I mean, that'd be a very tricky thing to solve. Probably just have to graph and get there as accurate as we could. But because of this theorem, I can prove that it exists. If we want to look for it, we can find it, to some level of accuracy, but we know it exists.
So intermediate value theorem is used for finding the root.
No, because I'm not finding it, right?
Oh, well, proving that it exists.
Right, proving it exists. And I want one thing you said for finding roots. It's not for finding roots. It can be, but it's for finding. So by the same logic, I also could have proved to you that that function equals 10 somewhere on the 0, 1 interval, right? So we use it to prove that a root exists, but really I could also say that, any number between -1 and 13 has to exist for this function on the interval.
Okay, so what you're saying is for like for the chunk of x values that we're looking at for this function,
Mhm.
we can determine like on that range what y values are possible along.
Not only possible, but certain. to exist.
Okay.
Everything, pick your favorite number between -1 and 13, and we have proven that the function takes that value.
Okay.
On the-
That's something.
So that's the purpose of this theorem, right?
Yeah, to prove those things exist, and maybe I can give you let's try to give a counterexample here. Let's figure out what f of 2 is. Let's do this. F of -1 will be easier for me to do in my head. F of -1 is -5 plus 17, 19. So I have f of 1 equals 19, right? That's not gonna do what I wanted. Maybe I really do want f of 2. I might need some help. I got 367, I'm pretty sure that's right.
Yes.
Okay, cool. Is there a root on this function between 1 and 2? Yes or no? So f of 1 is 13, f of 2 is 367. So I got to know.
So you're asking if I like that theorem exists.
So basically, I'm asking, is there a root on the open interval from x equals 1 to x equals 2? So I'm hearing a lot of people say no, and the real answer is maybe. I just can't prove to you that there's a root there. I'd have to do something deeper. So and here's kind of a pitfall with this theorem, or at least with people thinking about it. Let's look at something general. Here's A, here's B, endpoint, endpoint. It would be tempting to say that there's no roots on that interval, right? But unless you have a really good idea how that function behaves, you don't know that it doesn't do something like that. So that's why I'm saying for this function that I gave you on the interval from 1 to 2, there might be a root. You just can't guarantee to me that there is one. As opposed to the interval from 0 to 1, I can absolutely guarantee it for you. This theorem makes it bulletproof. Yeah.
So it's back to the original example where the -1 is the other thing we're making.
Yes, there's no way you can say no. Just can't guarantee it for me. Any questions about this thing here? Go ahead.
Why again do we use the open interval instead of closed?
Let's replace this function here with this. Let's say instead of some kind of curve, it's a perfectly straight line. The reason we do the open interval is, let's say this point right here is 1, 1, and this point right here is 8, 4. if I'm only looking at y values that are strictly between 1 and 4, then the x values that we're going to give those are going to have to be strictly between 1 and 8. Because if I try to prove, or if I try to use this theorem on the closed interval, it's not going to work, because if that's a straight line, then I don't actually reach y equals 1 or y equals 4 on the open interval. That makes sense?
Yeah.
Okay. Anything else? All right, that is all I have for you for 1.5. Was there a question about intermediate value theorem on the quiz?
Yeah.
Okay, I cannot make it do today. I forgot I had that on there. Let's do Monday night. Cool. Okay.
So,
Should I take it back?
Yeah, unless you have some kind of idea how to do that.
I think maybe, I don't know.
You want it back?
Yes.
Okay. Thank you. Sorry about that.
so we just like resubmit on the.
Yeah, I mean, unless you're happy with it the way it is, it's set up for unlimited submission, so you can just go back and redo it. All right, so section 1.6 is about limits involving infinity. All right, we've talked about this function quite a bit before. Does this limit exist? I mean, we have said this exact thing.
Yes.
I got to vote for yes. Does this limit exist?
No.
No. So it's tempting to say that it exists if I say that it equals something, right? But for a limit to exist, what does the limit have to equal?
One singular.
A singular real number, which infinity is not. So this limit does not exist, but I'm telling you something about how it behaves. How about this limit? If the limit of that top function is infinity, yeah, this one, so as x gets closer and closer to 2 in that upper function, x is, or y is going to get very, very large. In this other function, y is going to get arbitrarily small. So negative infinity is that limit. Pick whatever negative number you want, no matter how far away it is from 0. I'll be able to pick an x value that delivers it. So neither of these limits exist, but I can tell you a little something about how the function behaves around x equals 2 by saying the limits are infinity and negative infinity. So you've probably seen this word before, asymptotes, especially when you're drawing graphs of certain kinds of functions. Graphically speaking, an asymptote is a line that a graph approaches but never achieves, never reaches. Or another way to think of it, the distance between the line, that line, usually a vertical or horizontal line, and the graph is always positive, but I can make it as small as I want. So vertical asymptote. So vertical asymptote, some x equals a line. You're going to have a vertical asymptote if one of these is true. If your limit as x gets closer to a of some function is, it does not matter if it's positive or negative infinity. You're going to have a vertical asymptote in either case. Or if it's just a one-sided limit. So if any of those conditions are met, or as you approach a from either side or both sides, the function goes to positive or negative infinity, you have a vertical asymptote. And with the function we just looked at, that 1 over x minus 2 squared definitely fits one of these. Any questions so far? All right, so let's think about this function here. 1/t minus 1. What is the limit of the limit of this function as t approaches 1 from the left? First of all, is this function defined at t equals 1? No. So can't really go about it that way. So how can we think about the limit? So the limit as t approaches 1 from the left of f of t. It's a rational function, but it's not defined for t equals 1, so we can't just use that. How else can we think about, or how else can we examine what this function is doing? What was that? Values close to 1? So what are some good values to use?
0.9.
So for this specific limit, I can't use both of those. Why not?
Oh, I was coming from the left.
Right.
0.9.
So let's do these couple things. So 0.9, 0.99, 0.999, see what happens. So 1/0.9 minus 1 is going to be -10. Should be -10, -100, -1000, right? So the closer we get to 1 from the left, what is this function doing? Going towards -infinity, right? So the magnitudes are getting larger and larger, but they're getting less and less. So this limit is -infinity. So at this moment, can we already say this function has a vertical asymptote?
Yes.
Yeah, we can already say that. But let's try to get some more information. What about as t approaches 1 from the right?
It should be positive 1,000, but 0.11.
Right.
1.1, 1.11, 1.111.
Actually, 1.1, 1.01. I mean, we could use the numbers you said, but in keeping with the parallels here, I believe these are going to give me 10, 100, and 1,000. So are we okay with the idea that this limit is positive infinity? And if you want to kind of see what this is going to look like, where's that vertical asymptote going to be? So yeah, at my x value or my t value of 1, we know that as we approach that from the left, we're going to get this kind of behavior. As we approach it from the right, it's going to blow up to infinity. Any questions on this? Does it look kind of familiar? All right. Find the vertical asymptotes of this thing. Y equals cosecant of x. Do you remember what cosecant means? It's 1 over something, right? 1 over sine. So we're looking at 1 over sine, right? So I think we'd all rather think about this in terms of sines and cosines if we can. So now I'm really looking for this. Where are the vertical asymptotes of this thing? What would cause vertical asymptotes to exist?
Can you do that with something?
What's that?
Can you cause a vertical asymptote?
If it was just sine of x, I could not, but this is 1 over sine x, right?
Oh, you're gonna think
And so what I'm really asking you for, yes, is where does sine of x equal 0? So sine of x equals 0, where does that happen? Just give me, I mean, it happens infinitely many places, but go ahead and throw one x value at me. 2 pi? Yeah, so I mean, it's, I'm hearing even pi, right? Is it really, is it just even multiples? I mean, it's odd multiples too, right? It's every integer multiple of pi. So sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. So the vertical asymptotes of this thing are going to happen. Basically, all these x values I just wrote down, x equals, let's just say in order, x equals pi, 2 pi, 3 pi. Those are all going to be vertical asymptotes of this function. So another way you can say that is this. X equals k pi. K is an integer. We okay with this? Have we seen this graph before? It's not terribly important what it looks like, but if you were to like go to Desmos or something and graph this, you would see that it would look a little bit like the sine graph, but you would see vertical asymptotes at very irregular pi intervals there. Any questions about that?
Those just going off of stuff that I probably should remember from trade stuff.
So
So like, how do you know that sine of x is equal to 0 at 2 pi?
okay, so I can talk about that.
Or should
So I will let you off the hook a little bit. There's a big difference between things you've seen and things that you definitely should remember, right?
Uh-huh.
Just because you've seen it doesn't mean that you're not a computer. You're not going to hold on to everything the first time you look at it. But like quick crash course in why that's true. Unit circle. Pretend it's a circle. Here's an angle, right? Here's some generic point. By definition, what the sine of an angle is every angle projects a point onto the unit circle. The sine of that angle is whatever the vertical distance is from the x-axis. So if you're okay with that, think about what this angle would have to be for the y value to be 0. It would have to be 0 pi or 1 pi or 2 pi. So every half turn around the circle is going to give you a y equals 0. Good question. And trig is one of those things that I feel like I really understood it really well. Like the second year I taught it in high school. It's one of those things you just kind of have to keep banging your head against it. So yes, keep reviewing it. Give yourself a little grace if it's still confusing you. All right, so I'm showing you a graph here of e to the negative x plus 1. So what we just looked at was as x approaches a real number, we saw some examples where y approaches, or y gets really, really large, or y gets really, really small. Now let's think about kind of a related but different idea. What happens as x hits really, really large? So in this function, what happens to the function f as x gets very, very, very large? Go ahead.
It just keeps like going down faster.
It doesn't keep going down, right? So let's answer this. As x gets really, like, when I say x is getting larger and larger, where should your eyes be going on the graph? Right. To the right, right? So as I trace this graph to the right, is that limiting? Is that going towards some limit?
Yeah.
Yeah, the y value would it's honing in on something, right? Do you have a question?
Closer to 1.
It's closer to 1, right? We okay with that idea? It might be, you might not be able to see exactly what this is getting closer and closer to, but hopefully you can see that it has a limit, right? So we have one proposal that it might be 1. Let's look at this function a different way. I can also say 1 over e to the x plus 1, right? As x gets really, really big, what's e to the x? And this is, by the way, what I'm doing here, I think this is a pretty good technique for thinking about limits, is think about what happens as, all right, I know that x is going to get really, really big, right? If I take e, which is just a number, it's a constant number, and raise it to larger and larger powers, what's it going to do? It's going to get bigger, right? Yeah, all your instincts. if I divide 1 by this thing that's just growing and growing and growing, it's gonna get super tiny. Is it gonna have a limit? If I divide 1, a constant, by something that's growing and growing and growing, so yes, it's gonna get smaller, but it's gonna trend towards something, right? It's always gonna be positive, right? So it's gonna get closer and closer to 0. And then the last step, which is probably the easiest step, what if I take that thing that's getting really, really close to 0 and add 1 to it? Getting closer and closer to 1, right? So, and by the way, none of that right there is like, mathematically rigorous or like, that's not a proof. But if you can convince yourself of it, like you're on your way. So yes, I agree. This limit as x approaches, or sorry, as x gets really, really large is 1. So here's how we can write that. The limit as x goes to infinity of f of x is equal to 1. Does this function ever equal 1? It won't. I can get it as close to 1 as I want, but I can't ever achieve it. Does this function have an asymptote? What is it?
Y equals 1.
Yep. In stereo.
Are limits and asymptotes the same thing?
Not necessarily. Keep in mind, until this section, we've talked about lots of limits, right? But in very few of the graphs I've drawn for you, we've had asymptotes, right? So maybe that's a good question to ask now. What are all these limits we've talked about in the last like 20, 30 minutes? What have they all had in common? The idea of infinity, right? I'm either letting x grow without bound, or I'm looking at what happens when y grows without bound. So, and that's really what an asymptote is. Like in this case, my horizontal asymptote is y equals 1, because I can just draw a horizontal line here that extends really left and right infinitely. And I have a function that gets closer and closer and closer to it, which will never, ever achieve it. So it's really only when you talk about limits that involve infinity in some way in one of the variables. Which I think is a good transition to what we're talking about here. So this is, I basically just copied and pasted this slide from the last one. I mean, asymptote is an asymptote, but we're speaking generally about asymptotes. The definition is the same, it's just how it manifests vertically or horizontally, it's a little different. A horizontal line, y equals L, I think what I say, x equals a for a vertical. So a horizontal line is some y equals a real number. It's a horizontal asymptote if one of these things is true. And really, now where does the infinity show up in this limit operator? As x approaches something, right? As opposed to a vertical asymptotes, it was, what kind of thing was x approaching? It was, yeah, x approaches some real number, y blows up to infinity or to negative infinity. Oh, sorry, I'm gonna go back. So as x approaches infinity, the function goes to a value, or as x approaches negative infinity. So for example, with the last function we just looked at, that exponential curve, the limit as x approaches infinity was 1, right? We didn't really talk about it. The limit as x approaches negative infinity is not 1. So these things don't both need to be true. In fact, they very rarely will be. Any questions on any of the definitions or the distinction between horizontal and vertical? So let's talk about these. So let's just talk about the first one first. So usually I take, I mean, until now pretty much, or until recently, I've taken some base value of x, some real number, and I try to think about what's going to happen as x gets close to that neighborhood. Doesn't really make sense to say that x is getting into the neighborhood of infinity. So when I say x is going, you see that x to infinity, that arrow there, what is that What does that tell us that we're doing, or what we should be thinking about? What's X doing? What was that? It's just getting bigger, right? Until when? It's just getting bigger. And the mathematical phrase you're throwing around is without bound, like, we're not stopping. So as X gets larger and larger and larger, what do we think one divided by that thing is going to do? Get smaller and smaller and smaller, so we're like the limit is negative infinity. Yes, right. So that's a key distinction here, is because getting smaller and smaller, I mean, I think I know what you mean, but I want to make sure that I do. Right. So it gets smaller, but it has a bound, right? It's not ever going to become negative. But yeah, I can, if you give me the smallest positive number you can think of, I can find an X, or 1 divided by that gives me your number.
Why does it have to be a positive number? If you, like, say if X approaches infinity, right?
Yeah.
Would it say, like, if you started looking at a graph of X equals -2 to infinity, would that still be approaching?
And this is a really good distinction, a really good question that actually came up for many of you who are here. But when we're talking about limits, you're really only looking at what happens as you get, and it's such a vague word when you say near some X value. So yeah, if you start at -2, you're right, it should be negative, but I don't care. I only care about what happens when X is getting, in the vicinity. So we're gonna think of the vicinity of infinity, because that's not a place, it's not a number. But I really only care about very large values of X. Because of that, what's going on at X equals like -1 or -2 doesn't affect this. That's a good question now. And that's, yeah, like I said, I mean, that kind of came up organically before class. What if we go the other way? As X gets smaller and smaller without bound, what's this limit going to be? What was that? Giant. It's also 0, right? So, and that's not quite as intuitive, I don't think. So I'm still dividing 1 by numbers whose magnitudes are very, very large, right? So I would expect my results to be very close to 0. Are they going to be positive or negative? Negative, but they're getting larger and larger and larger, kind of settling out towards 0, as you said. So where do we have an asymptote? Y equals 0, right? So coinciding with the x-axis, I have this y equals 0 asymptote. Do I have any vertical asymptotes? Go ahead. But what equals 0 for when I'm talking vertical asymptotes? X value, right? So I have a vertical asymptote at x equals 0. I have a horizontal asymptote at y equals 0. So basically, my y-axis and my x-axis are both serving as asymptotes here. So let's try to fill in the rest of this graph, knowing that I have kind of like these keep away lines that I can never achieve. And you've already answered this question for me. When x is positive, what does that mean about y? Sorry, let me be more clear. When x is any positive number, is y going to be positive or negative? Positive, right? So as x gets closer and closer to 0 from the right, y is going to get larger and larger. And when x gets larger and larger, as you said, y is going to get closer to 0. So you have this following both these asymptotes here. Very similar curve, just reflected over the origin on the left-hand side of the y-axis. So as you said, when x is positive, dividing 1 by that is not going to change the sign. Same thing on the negative side. If you divide a positive number 1 by a negative number, you're going to get a negative number back. And the further you go to the left, the closer those y values are going to be towards 0.
But can you determine like a horizontal asymptote that, x equals 0, like,
Y equals 0.
y equals 0,
Mhm.
by looking at the function, like 1 over x, how would you determine like, y equals 0 to the horizontal 0?
In general, and I'll go back to my last slide here. So when we're thinking about horizontal asymptotes, the question you're really after is, one of these two things. What's my function doing if x gets incredibly large or incredibly small? So, and that's really what we did with the 1 over x. With the 1 over x function we just looked at, the horizontal asymptotes come from, I'm asking what's the function doing as x gets very large or very, very small? As opposed to that, when I was talking about the vertical asymptotes, what was I looking at to talk about the vertical asymptotes here? Or how did we find them? Or how did we find the 1? So somebody told me pretty quickly that a vertical asymptote happens at x equals 0. How do we know that here?
No, just the more you study it, the higher the number. You get smaller and smaller bits and then you approach it.
Right, but how do we know? So that's true. So yeah, as you divide 1 by smaller and smaller numbers around 0, the magnitudes are gonna get really large. Either very large positive or very large negative. But another way we knew the vertical asymptote was there was, so this is a rational function, right? 1 over x. Those are continuous everywhere except where? Wherever the denominator is 0, right? So that's another way you can identify vertical asymptotes.
Yeah, I'm gonna ask you, I don't know, that's.
Oh, you're fine. It's worth talking about both. Any other questions? All right, let's find horizontal asymptotes for this thing. So, as we just said, what are we looking at? But if I want to know where horizontal asymptotes are, what am I really looking at? Like, what variable do I care about? What do I want it to do? Think about, obviously very different things. But we just looked at the function 1 over x, right? When we talked about its horizontal asymptotes, what kind of investigation did we do?
Look as it went to closer to infinity,
As what went closer to infinity?
x size.
As x went closer to infinity, right? So let's do that with this thing. So the limit as x gets closer and closer to infinity of f of x. And let's make sure we do both. Is it clear what happens? Is it clear just from looking at that function what's going on as x gets larger and larger and larger? So let's do this a couple different ways. We'll do it in a kind of intuitive, hand wavy, not really mathematical way, and then we'll formalize it a little bit. Let's just look at the numerator, 8x cubed plus 2x plus 1. As x gets really, really big, think about those 3 terms. What's the 1 going to do as x gets really, really big? You're just adding 1 to something that's getting more and more massive, right? It almost doesn't matter. So the larger x gets, the more 1 just becomes negligible. But couldn't you say the same thing about 2x as well? I mean, I'm cubing x and then multiplying that by 8, as opposed to just taking x and just doubling it. So basically what I'm suggesting is that only the largest power is going to, basically as x gets really, really large, the largest power of x is going to overwhelm everything else. Does that make sense? I mean, it's kind of wishy-washy and very intentionally it is, but I just want to kind of make sure we're okay with the rationale. Did you have a question?
Oh, I just remembered that rule.
Okay, I mean, calling it a rule is even kind of charitable. We'll do something a little more sophisticated, but I say that to kind of build up to what I'm about to do. Also, in the denominator, we okay with the same kind of idea? Especially since all you have is a variable and a constant. The thing that has the variable in it, as x gets really, really big, that's just gonna overwhelm the negative 147, right? So not the most rigorous way to go about it, but kind of helps you convince yourself of what I'm about to show you. Think back to the limit laws we did last week. Can I just break this thing up and use the limits that way? Like, for example, can I just say the limit as x approaches infinity of 8x cubed plus 2x plus 1 over the limit as x approaches infinity of 16x cubed minus 147? Is that something I can do? It seems like I should, but I can't. And here's the thing that I want to remind you about those limit laws. If I want to use those limit laws to kind of break these things down, then the individual limits have to exist. What's going to happen to this three-term expression here as x gets really, really big? Go ahead. It just gets bigger and bigger, right? So that limit doesn't exist. So I can't use those, but here's what I can do. I can multiply this expression, both numerator and denominator, by 1 over x cubed. And when I do that, let's see what happens. This becomes 8 plus 2 over x squared plus 1 over x cubed over 16 minus 147 over x cubed. Now let's try the limit law thing again. Are we okay with what I did?
That was just to cancel out the x cubed on the top and bottom, right?
Not even in the top and bottom, really, just like, I mean, really what I did was I divided the numerator and denominator by x cubed.
Okay.
Which basically I reduced the power of x on every single term by 3, which is totally legal.
And you chose 3 just because that was the base power.
Yeah. Because now what does that do for the limit laws for me? As x approaches infinity, what is 1 over x cubed going to go towards? That exists. What does this go towards? 2 over x squared. 0, that exists. 8 is a constant. What's the 147 over x cubed going to go towards? 0. So I have 5 individual limits that all exist, right? So didn't really change the function, just rewrote or re-expressed it in a way that allows me to do this. Basically, this is equal to 8 plus 0 over 16 minus 0, 1/2. So that's the limit. What does that tell us about where the horizontal asymptote would be for this function? Right.
So why did you put zeros for where the
Basically,
all the limits there?
I have 5 terms there, right? I was just taking the limits of all 5 of them.
Okay.
And again, the reason that I'm allowed to do that, as opposed to the one where I crossed out, these 5 limits exist. Some of these don't. Because that goes to infinity, that goes to infinity, that's just 1. But as long as one of them doesn't exist, I can't break anything out. How are we doing?
We just like explained what my high school teachers never did about why you can do the.
That's why I'm here, man.
About why you can do the for like largest exponent for the numerator and denominator, which is 5 fractions.
And the reason I'm showing it to you is because not all things are polynomials. And having that kind of trick gets you into trouble when you look at functions that don't look like polynomials do. I know that sounds mysterious. It'll make more sense when I have examples to show you that fit that mold. Any last minute questions? All right, everyone, have a good weekend. I'll see you Monday.